I'm Yidan from RIT. I will share our paper TraCS trajectory collection in continuous space under local differential privacy. So it focuses on trajectory collection, but in continuous space. Trajectory collection is a classical problem because trajectories they are generally sensitive, like daily routine, wearable sensor trajectories. There are two kinds of trajectories. One is that their locations are from a discrete location space, like these labels. The other is that their locations are from a continuous location space. It can be real number coordinates. These trajectories are collected by untrusted third parties for location-based services. So to preserve user trajectory's privacy, we can LDPify a trajectory. That means we can perturb a trajectory with LDP guarantee so that the adversary cannot distinguish sensitive location tau 1 from tau 2 within a given location space. So for this target, we want an LDP mechanism that for the given location space, they should first provide provable privacy for users' trajectories in both continuous space and discrete spaces. Also, it should have as high trajectory utility as possible. Most existing LDP mechanisms for trajectory collection are for discrete spaces. That means the discrete location space is either a point of interest or this discrete has the cells. Most of them use the exponential mechanism. So for each location, this mechanism will sample a noisy location based on the pairwise distance. Like these examples, so the noisy trajectory may look like this. Here we observe three limitations. One is the efficiency. So for the exponential mechanism, we can see that each sample cost On, where n is the number of locations in the location space. Because if we want to sample a noisy location, we need to compare the CDF of the random number. Then is the trajectory utility. It will decrease as n increases because each location will take over a part of probability. And applicability, it cannot apply to continuous location spaces. So to address these three limitations, we claim that operating on a continuous space is better and more universal. So for example, in this continuous location space, we can design simple sampling mechanism. For example, if we want to perturb this location, we can sample a noisy location from this red area with a higher probability. Otherwise, in this gray area, we have a lower sampling probability. So intuitively, there are three benefits. First, the efficiency. The sampling complexity is O1 because this sample is very easy. And for trajectory utility, this mechanism does not depend on the number of locations. And for applicability, it is applicable to both continuous space and discrete spaces. Because for discrete spaces, we can round to the nearest discrete location. This is a post-processing that not affect privacy. So having this idea, we then design two mechanisms for trajectory collection in continuous space. TraCS-D is a direction distance perturbation mechanism, and TraCS-C is a coordinates perturbation mechanism. Key idea is to decompose the two-dimensional location space into two subspaces. So for this location space, it can be represented by a Dirac space, then composed with a distant space, or it can be represented by two distant spaces. Then we can design a one-dimensional mechanism for each subspace. So then let's see how to design one-dimensional LDP mechanisms for direction preparation and distance preparation. We leverage the existing piecewise-based mechanism, but other LDP mechanisms for such bounded numerical domain are also applicable. Here are two examples. So for such direction space, if the true direction is 0, then within this arc, it has a higher sampling probability, otherwise a lower sampling probability. So this is for linear distance space. Then we can see evaluations. Our claims are that in continuous spaces, our mechanisms have better utility than naive baselines like Planar Laplace plus truncation. On discrete spaces, our mechanisms should have better efficiency and utility than existing methods. There are many mechanisms like ATP, N-gram, LSR, etc. These mechanisms are designed for discrete location spaces, but they are much smarter. So for ATP, the key idea is direction prediction. So let's see this example. So when perturbing this location, first we will divide the direction space into sectors. For example, 4 sectors, 1, 2, 3, 4 sectors. So this is the sensitive direction. Then we can perturb the sensitive direction with high probability. The perturbed noisy sector is the same as the true sector. So it can reduce the location space into a small area. Then we can apply a potential mechanism into this area. For N-gram, the key idea is the reachability constraint from public knowledge. Reachability means that from one location to the next location, the distance cannot be too far. So this is a reachability constraint, and we can apply the LDP mechanism. We can apply the potential mechanism to this reduced reachable area. So we can see evaluations first on continuous spaces, and we first focus on average error utility metric. We can see that our mechanisms, this red line and blue line, they have lower error when epsilon becomes larger. On real-world data sets, we have this Tokyo location space and Chicago location space. So in this context, our mechanism focuses on this rectangular area. And we can see that the error of our mechanisms, they still have a lower error when epsilon becomes larger. Then on discrete location spaces, so here the discrete location spaces are these blue points. So for our mechanism, it first particular location in the continuous space, then rounding to the nearest location. This is the post-processing. Here are the error plots. So we can see our mechanisms, their error is not as good as in continuous space, but still it has lower error when epsilon becomes larger. For efficiency, our mechanism have significant advantage because it has one complexity compared with these mechanisms using exponential mechanism. So in summary, this paper focuses on trajectory collection under LDP. We show that operating in continuous space can do better. Thank you for your listening.